Hey there everyone! In this video we are going to be covering the PentesterLab rack cookies and commands injection exercise. The goal of this exercise is to gain command execution on the web server through privilege escalation and cookie tampering. Before we get started, let's cover some prerequisites. If you want to follow along with the exercise, you'll need the ISO of the vulnerable web app, which can be found on the PentesterLab site. You'll also need some way to host the vulnerable site. I'm running a VM locally on my machine with VirtualBox. If you don't know how to set up VMs with port forwarding, I'll have a link to a tutorial in the description below. You'll also need a working knowledge of Python and Ruby to write the scripts in this exercise that will exploit the vulnerabilities. With that out of the way, let's get started. The first step for any exploit is to examine the target site and gather information about it. Let's do that now. For my setup, the site can be found at localhost 8000. When we arrive, we're redirected to an authentication page. Let's pull up the Network tab in Developer Tools and see what happens when we try to log in. On Chrome, to access the Developer Tools, use Ctrl-Shift-I. Now let's try to log in with some basic default credentials. Admin, password, and hope we get lucky. Press Enter. So pulling up the request, it appears that when we hit the login button, we issue a post request with two parameters, login and password. We can also see that since we failed to authenticate, the server responded with a 302 redirect status, which redirected us back to the login page. Also, the response headers from this request reveal a lot of information about the server itself. We can see that the server is running Apache version 2.216 and is powered by a Fusion Passenger version 3.0.12. The mod Rails annotation here seems to hint to me that we're also dealing with a Ruby application. It's also a good idea at this point. We should take notes of the details we just discovered, since they may reveal possible attack vectors later on. And also, we should examine the source code of the page itself. I've already done both these things, and investigating the source code revealed nothing new. So at this point, our current plan of attack will be to try and brute force the authentication page, so we can hopefully gather more information about the application. Now, there are multiple ways to brute force a page. You can do it manually, test password 1234, and be here forever. Or you can write a simple Python script to try a bunch of different credentials and see if any of them work. Even easier than that, you can use someone else's script. Just Google brute force HTTP login and take your pick. And I went ahead and wrote my own script before this video. This script, let's pull it up now, bruteforce.py. It will asynchronously conduct a dictionary attack on the HTTP endpoint I specify. By the way, the source code for this and everything else we write will be available on my GitHub. To perform a dictionary attack, we need a good dictionary of words. I already downloaded a sizable word list, but if you want your own, just Google password list and you'll have thousands to choose from. So let's try and crack that login page. It's going to pull up a terminal, and I already forgot the command args. So let's do a --help, and then so bruteforce.py, give it the URL of the authentication page. So HTTP localhost 8000 login, then the word list .txt dash u is credentials that we wanted to test against, basically another word list. The method will be post requests, and then the parameters are the login parameter and the password parameter, and then the number of threads that we want it to run in. So let's just do it on 10. Let's let it work its magic. And it's thinking, still thinking. The word list I provided has about a million entries in it. So as you can see, brute forcing a page does not scale very well. But if they have predictable passwords like test and test, which we authenticated with, it can be an option. Now let's take these credentials we just received and try to make sure we can log in with them. Test, test, and cool. We logged in. LastPass trying to help me out, but I don't need its help. Let's see what we can do here. Um, that just takes us back to the page. We can log out. Home page. We can inspect the source code. Let's just go here. Index. And nothing is really standing out to me. There's no script tags or there's no input from the user whatsoever. So let's see what else we can find. Maybe they issued us a cookie, and they did. So this is promising. So we should copy this cookie into a local file and see what we can do with it. Maybe we can reverse engineer it and then maybe tamper it with it. Let's copy that into cookie.txt. Cat cookie, make sure everything's good. And looks like we have it. So let's go back to the browser. The cookie name was rack.session, which sounds awfully like a default cookie name. So let's Google rack.session and see what we get. Cool. Looks like we have documentation for the cookie. And better yet, we have source code. Let's take a look at the documentation first. So it says that rack session cookie provides session management, and that the session is stored as a base64 encoded Marshall dataset. We'll go over what that means in a bit. This is an important bit right here. When the secret key is set, cookie data is checked for data integrity. And here's some code examples of how all that works. So let's take a peek at the source code now and see how all this comes together. So here's the source code. Let's scroll down. Okay, so here's the cookie class, and it has a few, where'd it go? Few internal classes. Base64 class, which looks like it just uses the base64 library to encode a string, and then a Marshall class, which inherits from base64, and then encodes the string by marshalling it first, and then calling the parent's base64 encode method. So it'll marshal it, base64 code it. And marshalling is similar to pickling in Python. It basically serializes the object into a byte stream. The cool thing for us about these operations is that they're both invertible, which means we'll be able to write a Ruby script that can decode our cookie and see what data was encoded in the first place. So let's peek the constructor, which in Ruby is called the initialize method. And we have a few instance variables for the cookie class. It looks like we have secrets, coder, which is how it's being encoded, which is that base64 Marshall encoding scheme, and also HMAC. HMAC stands for hash-based message authentication code, and is generally used to verify both the data integrity of a message and the authenticity of a message, or cookie in our case. And it looks like by default, if we look at this fetch method, that the default way to generate the HMAC is with the OpenSSL SHA-1 encryption. For now, let's squirrel away that information and see if we can write a script to tamper with our cookie instead. So let's go back to your favorite text editor and create a file. Let's call it tampercookie.rb and open it up. And let's start writing some code. First, create a function. We'll call it a decode cookie. I'll take in a cookie, a C, as an argument. And we need to split the cookie up into two parts, the data part and the HMAC part. We only want to decode the data part for now. So if you go back to the source code and you scroll down, you can see here that the cookie is partitioned into two parts and is delimited by this double dash dash part right here. So if we examine our cookie too, cat cookie.txt, we can see that all this right here, that's the data that got Marshall base64 encoded. And this last bit right here, that's the HMAC. So we don't want to try to crack that just quite yet. We need to reverse the encoding on the data part first, and then see if we can crack that HMAC later. So we'll do cookie equals c dot split, and we'll split at that delimiter, and then we'll say that the object is first it was it's URL encoded, so we'll need to do URI.decode cookie, the first bit, and then it's base64 decode, and then lastly the first thing it did, so we're kind of peeling the onion and then trying to get back to the center, which is it was first marshaled. So we'll do marshal dot load all that. So in the rack.sessions source code, it went like this: marshal serialization base64 encoded, then finally URL encoded for the browser. And then what we'll do is we'll do pretty print that object just to see what happens. And we'll need a few modules, so we'll do require URI and pretty print, and then I think we need the base64 module, and of course end this function. And lastly, we'll create a main driver. I'll take in the cookie file as the argument list. So if argv.length does not equal 1, puts usage tamper cookie file. And then of course return 1 for error end. And then we'll open up the provided cookie file, cookies equal io dot readlines argv sub 0. We'll just chomp off the extra white space. And for cookie and cookies, decode cookie. That function we just made, decode cookie. And then call our function. And oh, it looks like I have a typo. And I'm not the most proficient Ruby programmer. In fact, I learned all of this to get through this exercise. But so if anything seems kind of off keel, that's kind of why. So let's run the script we just wrote. Do Ruby tamper cookie, and then give it the cookie that we stored the data into, and we get an error. And this is actually a good thing. So what happens is when Marshall tries to create a Ruby object out of the cookie data we provided, we get this argument error that there's an undefined class module user. On the server, when the cookie was first marshaled, it serialized this user class, and since we don't have a user class defined in our code, we get an argument error. So it's actually an easy fix. What we'll need to do is just define a stub for this user class and get around that error. Okay, let's try again. Oh, I must not have saved it. Try it again. All right, so now we get a different error. It says undefined class module data mapper. And data mapper is actually a database abstraction library for Ruby. So all we'll have to do is just import that module data underscore mapper. Save this time and run the script again. And now another error, but at least it's different. This time is complaining that we don't have a SQLite adapter defined. So after some research on Stack Overflow, turns out the solution is actually really easy. We just need to define a default adapter like so. We'll do data mapper.setup default SQLite 3 memory. And now let's run the script again. And awesome, we've successfully reverse engineered our cookie. So let's take a look. So here's our session ID, and here's the user class and all of its instance variables. If you notice, there's this handy little flag right here that says admin, and right now it's set to false. So let's go ahead and try to set that to true, re-encode our data into a cookie, and see if we can get admin privileges on the site. So to do that, let's modify our stub first. We'll need to access that admin flag, admin, and then we'll create a new function. We'll call it a encode object. I don't know if I can spell. And then what we'll do is we'll modify that flag parameter first. Admin equals true. And then we'll do basically the exact opposite, well, the inverse of this operation right here. So we'll say encoded is URI dot encode base 64 dot encode 64 Marshall dot dump object. Then we'll actually return this object and modify this decode cookie function as well to do the same. And we'll do all the printing in the main function. Return object. So decode cookie decodes the cookie, creates a object out of it and returns it, and then the main will pass off that object into encode object, at which point it will set the admin flag to true and then return to us a valid cookie. So we'll say object equals decode cookie, and then we'll just pre-print that object again. We'll say puts decoded cookie. And then we'll say the new cookie is encode object, the object, and then we'll say puts new, we'll say tampered cookie, and then it puts that new cookie. Actually, cool. So now let's run that script again. And here we have it, our new cookie. It's not quite all we need yet. So let's actually grab it and see if we can replace our cookie value in our browser with that and see what happens. So here I'm going to take that cookie, paste it in, the new cookie, paste the new cookie in. And actually, if I try to refresh the page, you'll notice I get logged out. And that's because we didn't attach the HMAC value back to our cookie. And the problem is we won't be able to attach the old HMAC value to our cookie because the data has been modified. So we'll fail to pass the data integrity check. So actually, if we let's take a look at the source code again and go back to the unpack cookie data. So this is how it verifies that our cookie is authentic and has not been modified. And what it does is it makes sure, it calls this digest match function. Basically takes the session data and compares that to the digest, which is the part that follows the dash dash, the HMAC. And the digest match function, if we go to it, basically says If there's any secrets, we're going to do the secure compare uh, with the digest that came with the cookie, and the digest that we're going to generate with this HMAC function. And what that does, this generate HMAC function, all it does is it hashes the secret data that's on the server with the data in the cookie. And if that returns the same thing that matches this digest, then we've passed the function, these compare cookie, unpack cookie data validation function, and that means the cookie's valid. So what we'll need to do is try to crack that old HMAC we got, cookie.txt. Try to crack this code and try to see if we can find out what the secret data is on the server so that we can sign our new cookie with that same secret data. So to find the secret data, we're going to write a script to brute force the HMAC value for us. Since we have this valid cookie, we can just take the data part and try to rehash that with a word in a dictionary and see if we generate the same HMAC. And if we generate the same HMAC, then we know that we have found the secret word. So I'm going to make a new script. I'm going to call it find secret.rb and close that out and open it up. And the first thing I'm going to do is actually literally copy and paste their generate HMAC function, because this is how they generate the HMAC. So I'm just going to match that. This at hmac.new, that's their instance variable. So we're going to have to, I believe their default was this OpenSSL digest SHA-1. So we'll copy that too, and then do the .new. And yep. So now we're going to create this new function, call it def find secret. We need to hash the cookie against a list of words. So say data signature equals cookie dot split. Then we'll say the data equals URI. We got URI decode it first. And then for every word in the word list, we want to see if we can match the signature. So we'll say if generate HMAC data word, equals signature, then we'll return the word that it matched against. That'll be the secret. And then if we finish this for loop, that means we didn't find the anything to match the signature, so we'll have to return nil. And that function. And then we'll write a quick driver in main real quick. Def main. And we'll take in the word list and the cookie as command line arguments. Usage find secret. We need the cookie and we need the word list. If we did not get that, we'll just return 1. Cookies equal, we'll do the same thing we did in the last script. Dot read lines argv sub 0. And the chomp just gets rid of that extra white space, which can be a problem if we're trying to parse all this. IO dot read lines argv sub 1. And then we'll say for cookie and cookies, secret equals find secret cookie words. And if secret dot nil, we'll say, which means we didn't find any secret words. We'll say, just put an error. Brute force failed. And otherwise, we will print out the secret word. Secret found. And then end that. And end that for loop. And then finally call our function. Oh, and lastly, we need to import the URI module and the OpenSSL module. So let's try and run the script. And I'm going to use the same word list that I used in the previous brute force algorithm. So we'll do Ruby find secret, and then we need the cookie and the word list. And the secret was found, and the secret is secret. So now that we have the secret word for the signing the cookie, we can sign our own tampered cookie and then attempt to modify the cookie in our browser and see if we can get the administrator privileges. So let's modify our tamper cookie script to also take in the secret word as a parameter. And then we'll decode the cookie as normal. And then when we encode the object, we'll have to pass in that secret word to attempt to sign it with that. And now let's go back up to the encode object, secret. And before we URI encode, we'll just name this actually data, because that's really what we're encoding. Before we encode that, we are going to append first generate the signature and then append that to the URI encoded data portion. So say signature equals generate HMAC data secret, and we're gonna actually literally copy and paste this function right here, and then we'll return the UI.encode data. And for some reason URI encode doesn't properly replace the equal character with the correct character, which is %3D. So I need to do that manually with gsub. Then we'll append the dash dash delimiter, and then finally append the signature. And if everything looks good, oh well, you know what? I think I need the OpenSSL import as well. So now if we try to run this, we can our tamper cookie script will now not only reverse engineer the cookie and modify the admin field, we will also sign it with the secret data, and hopefully that'll work in the web browser as well. So cookie.txt, and the last thing we need is the secret word, which is secret. Run that. We get this nice new tampered cookie with this HMAC at the end. And we'll just copy that into a file real quick. Call it admin cookie.txt. And now if we log in again to our vulnerable web app, and then we open up the developer tools and modify our rack.session value cookie. And then if we refresh the page, here's the moment of truth, see if everything works. And look, we got new options. We can edit and delete these entries, create new records, and that's because we successfully elevated our privileges to that of an administrator. So now what we need to do is try to poke around with this admin interface and see if we can detect any more vulnerabilities. So let's go ahead and start clicking on buttons. Let's click this webmail thing and see if we can maybe cause a SQL injection error with a colon, and it says invalid data provided. So let's actually open up the network tab and try to catch these post requests. So let's actually try to inject a new line, because a common problem with regex filters, especially in Ruby, is they're usually multi-line by default. So we can generally inject a command by using this new line character, arbitrary data like uname -a, and then see if that works and see what happens. Update. So it is a post request, goes to this update endpoint, and we attach our cookie in the request. So that's important. And it looks like we have this form data, ID, mail, and then the IP. So we're actually going to view the source of this. So if you see right here, the IP address where we attach the new line character, the URI encodes the slash and then it leaves in the end. So we need to actually create a request in Python or something so that we can properly URL encode the new line and see if we can get a command injection there. So let's write another script. Hopefully this will be our last one. Let's create, we'll call it command injection.py. And we're going to open that up. So this first draft is just going to be more of a proof that a vulnerability exists. See if we can execute any sort of command injection. So we'll do always import the request libraries for this type of stuff. And we'll give it the URL equals HTTP localhost 8000. And then we'll see if we can inject a command. So we'll create a function called inject command, and we'll need our cookie as a parameter because we'll need to attach that in our requests. And then we'll say the admin cookie is rack.session cookie. And then we'll create our payload. And so let's look at this request again. We'll do that. And we'll just kind of follow this format. So we're going to target this webmail entry. So we'll say ID is 1. The name is webmail. And the IP address, I'm kind of like all my colons to be lined up. And the IP address was 192.168.3.10. 192.168.3.10. And I'm not gonna do the new line and the command injection quite yet. I'm just gonna do see if everything actually works before I try to mess around with the request. Let's see, TTL was 600. And then we're going to say the response equals requests posts URL. Then we need to do that update endpoint. And we'll set our cookies to that admin cookie. And our data for the form is a payload. And then we're just going to reprint response.text. And then see what happens. So we'll create a little main driver name equals main len argv is not equal to. We'll just call a help function, which I'll write just real quick. I like having these help functions here, so when I come revisit this script months from now, I kind of know what command line arguments I need. Otherwise, I'll have to look at the source code. Admin cookie. And then we'll say, and then so we'll open this admin cookie sys.argv sub1 as file. Cookie equals file dot read. And then we'll again strip that white space. And then we'll try to inject that command with the cookie. And that should be it. We'll actually give it the G-bang so we can run this as a regular script. Use a bin environment Python 3. And let's try to run the script and see what response we get. So we'll open up another terminal and we'll say / command injection py, and we'll need the admin cookie. Admin cookie.ticks, and then we gotta make it executable. Then execute that again. And it looks like it worked. Yeah, so we got these edit and delete buttons. So we're actually on the admin interface. There was no warning. So what we can do, we'll just give it for comparison. See if we run it with the regular cookie.txt, see what happens. Yeah, so we're in the login page now because the regular cookie doesn't have access to that endpoint. So what we'll try to do now is run this with a new line and give it a sleep 5. So if this takes a while to execute, then we know we have command injection on the server, and that will lead to other things. So we'll do that. Save. Command. And it looks like it's taken a while, which is a good thing. That means we have command injection on the server. So since we have command injection on the server, what we'll really want is to kind of create some sort of pseudo shell so that we can really explore the server without having to manually enter commands right here and save the source code. So what I'm going to do is, the strategy what we're going to do is try to do our command, right? We'll make this a formatted string. And then we'll echo it, put the output of that command into some publicly reachable file. So like file. And so we need to find a spot in the server that's publicly reachable. So we know, if we go back here, that the sources, we know that we can reach these .css files. So a good place to store the output of the command will be in the same folder that these files are in. So we'll need to find that folder, and usually that's in a public folder. So first thing we're going to do is change this command, and we'll do an ls-a and see what we get. And if we look at the so we, for the alert message error, this is where this the output's currently getting outputted, and we only got this one entry because it looks like this source code, the HTML, is only outputting the first value. So we'll see if there is an ls. Well, ls the public folder. Let's see if it does exist. We'll scroll back up into the error message. If I can find the error message. Yeah, so we got this bootstrap.scss, which is the first entry in the public folder. Right? So what we're going to do is store the output into that folder, and then we'll pull down with a get request that the output of that file so that we can actually see what's going on. So let's modify this script. We'll say output file, and we'll name it something inconspicuous like .keep. And then the output path is for these type of applications using var. Actually, let's get a pwd so see what our working directory is. Pwd, and then where are we? Cool. So right here, this is URI encoded // so it's var dub, and we want the public. So we're gonna do output path var dub public. will be our output path. And then what we're going to do is say output equals output path plus output file. We'll do the same new line here with this backticks, and we'll say command, and we'll output that into the output file. We'll add another parameter to this as command. And then what we really want to do is make this whole loop interactive so that we can run multiple commands with one session. So what we'll do is under this, we'll create this new function called run shell, and it probably need our cookie. I'll say while true, command equals input command, get the command from the user, me, and then we'll get this response equals inject command, cookie command, and then we'll have to parse that to make sure everything worked out good. Beautiful. PEA soup resp.text. Give it the HTML parser, and then before I forget, let's import that module. So basically the reason we'll want to parse this is we want to make sure we're not like logged out or anything. So if we say if in new line, because that is invalid data provided in soup.find, and it was under the div class alert message error. Alert. This is what I'm trying to parse right here. Alert message error. We'll say print failed to process command. Else we're going to print the result of the command. So I'm going to need that function, create a function called get result, and all it's going to do is pull down that output file we got. Request.get URL plus out file text. And looking through this, oh, we need to actually return this request. In fact, we can just do a return statement right here. You know what, actually, sorry, I'm kind of all over the place. We'll run this request, but we don't want to leave a bunch of trail on the, make it immediately obvious on the web server. So what we'll do is actually undo the update since we already have the file, because we don't want to have a bunch of, so actually if you look at this right now, if I refresh it, you'll see that the last command I did is now publicly viewable right there. So you don't want to leave too much of a trail. Say payload, change the IP parameter back to its original IP, equals 192.168.3.10, and then we'll post that request again. Request.post plus I don't need to store this request, but then I'll return the original response from the command injection form of the payload. And then, let's see. And I think that will do everything we need. Got another. Oh, so for the main function, we're going to change this to run shell. So let's try and run this and see if we can get a pseudo interactive shell. Let's give it an ls. Oh, we got a name area. Yep, that'll do it. Oh my gosh. All right, let's try this again. Command ls. Cool. Look at that. We just got the entire contents of ls. We can do who am I, www. Print working directory. We can probably even modify files, delete them and everything. So we have the pseudo shell, and from there we can really do pretty much anything we want, especially setting up a reverse shell with netcat, which I'm not going to do in this video because I'm kind of running out of time. But if one thing we can definitely do is show the contents of their etc password folder, and look at that. We can even, let's see, we can look at the source code of this vulnerable web application as well. Here it is, the source code of this. Here it is, the post update endpoint. That's where this the command injection vulnerability is happening, is right here. So that will be the extent of this exploit. We were able to summarize, we were able to brute force the authentication page. I'm going to log out. Brute force an authentication page, get some credentials, reverse engineer the cookie they gave us to elevate our privileges, and then from there, probe the administrator interface to find a command injection vulnerability, and then create this pseudo shell program. And again, all the source code will be on my GitHub if you want to perform it yourself and follow along. Other than that, I hope you enjoyed the video, and please leave a comment.